Welcome, everyone, to the 12th Annual Life Sciences and Society Program Symposium. This is also, as you know, Saturday Morning Science for March 12th, 2016. This is a joint venture between both groups. Our first talk, we're having our first talk and major talk in the symposium today, but before we get started, I just wanted to let you know a little bit about what the symposium is and what we've been doing. So the Life Sciences and Society Program is a program that exists on campus. It's been around for about 12 or 13 years. The goal is to try to get interdisciplinary interactions going on and sort of outreach about science, communication about science, sort of throughout the university community and then also out to the community of Columbia and Mid-Missouri as well. This year, the committee chose to focus for the symposium on climate change because it's a really important issue of our time that a lot of people are dealing with. There's a lot of confusion out there about what the science is. So we're interested in talking about what the science is. We're interested in talking about what's happening with climate change, what it is, also why it's happening. But even more so, we thought it was really important and interesting to a lot of people to talk about what we should be doing about it. And so most of the talks in the symposium are going to have that element as well. So today is the first main talk, but I want to tell you about briefly the events happening next week. At 5:30 p.m. on Monday at Ragtag Cinema, we have a showing of Merchants of Doubt, which is a film about some of the climate change denial and the sort of controversy surrounding climate change in the press. That's free and open to the public, like all our events. At 12 noon on Wednesday in the Adams Conference Center in the Vet School, there's going to be a panel on conservation in the Anthropocene. And that's with a bunch of officials from the Department of Natural Resources and other places, so that's at 12 noon next Wednesday. Thursday night, here in this auditorium, Andrew Revkin of the New York Times, who's been an environmental reporter for over 30 years, is going to be here talking about his history reporting about climate change and the reactions to climate change in the press, etc., including how changes in the types of media we have changed the way it's reported and the way people have reacted to this kind of reporting. That's at 7 p.m. with a reception at 6 o'clock if you want to come earlier on Thursday the 17th. Friday the 18th, we have Marcia McNutt, who's a former head of the U.S. Geological Survey, current editor-in-chief of science, and also incoming president of the National Academy. She's going to be here speaking at 4 p.m., again here, and she's going to talk about climate change mitigation. She's headed 2 panels at the National Academy where they've investigated what should be done to try to slow climate change, and she's going to talk about what they found at that event, and then there'll be a reception following for those of you who want to stay. And then all day, Saturday the 19th, we're going to have 4 talks here. We have a little bit of food for you starting at 8:30. At 9 o'clock, Wes Jackson of the Land Institute in Kansas, who's been a big advocate for 30, 40 years on sustainable agriculture, is going to talk about agriculture and climate change, the interrelationship between the two and the implications for agriculture. And 10:30, so Saturday morning science time, just like this week, we have Marshall Shepard from the University of Georgia. He's former head of the American Meteorological Society, and he's going to talk about how to communicate about climate and climate change. And one of the things he talks about is slaying some of the zombies or kind of myths out there that exist about climate change. After that, we've got lunch for those of you who'd like to join us out in the atrium. At 2 p.m., we have George Luber from the Centers for Disease Control, and he's going to talk about health implications of climate change. And then at 3:30, we have Naomi Oreskes from Harvard. She's a historian of science. She's written the book Merchants of Doubt as well. She's written both strongly about the existence of a scientific consensus on climate change in Science Magazine and other places, and she's also written again about climate change denial and the controversy and what's happening with that. So we hope you join us for all or many of these events. And with that, I'd like to turn it over to Ken McLeod from the MU Department of Geological Sciences to introduce today's speaker.
Thanks, Mary. It's my distinct pleasure and honor to introduce Dr. Ali today. But first, thank you to the Life Science and Society program for bringing these speakers, and to all of you for coming out. Mary's introduction was great. The idea of having both the science and the policy presented in this symposium is something that Dr. Ali does all in one person. His list of accomplishments individually are truly impressive. He is the Evan Pugh Professor of Geology at Penn State University, published something like 250 primary research papers, 7 books, won every award that any society offers, honorary degrees. He is a elected member of the National Academy of Sciences, the American Academy of Arts and Sciences, and a foreign fellow of the Royal Society. He is also interfaced significantly with policy, testifying in front of Congress, both the Senate and the House. Vice President, participated in the IPCC second, third, and fourth iterations, including being the lead author on the glacial chapter in the fourth IPCC report, for which he was one of the shared recipients of the Nobel Prize. And he's also done an impressive amount of outreach activity. Lectures like this, numerous interviews, awards from educational societies, featured in and hosted several PBS shows. So I'll get out of the way and turn it over to Dr. Richard Allen.
Oh dear, oh dear. Thank you. It is such a pleasure to be here, and thank you to the Life Sciences for bringing this. You are in for a treat, so do try to come back for the rest of the events, because there's some fantastic things. Somebody should really work hard to try to get guitar for Andy Revkin on Thursday night. He used to play with Pete Seeger. He's very good, and he can do climate change. Your Saturday lineup is fantastic. And I want to thank Mary. I want to thank Ken, new friends and old here. It says something very nice about your community that so many of you came out on a gray morning to hear about a subject which can be a little depressing somehow. What I intend to do, I hope, is walk you through a story this morning about just how much we love our energy system, just how unsustainable it is. I want to scare the pants off of you, and then I want to leave you with something which is really empowering and really forward-looking. And I believe what I'm going to tell you is the best scholarship, but with a little spin that is informed by a bunch of students. So with that as a take, I'm going to start you off by doing a little bit from some research I've done. So let's head to Greenland first. If you ever get the chance to go to Greenland, I recommend it. It is a fascinating undertaking. The wildlife on the coast is really amazing. You know, here's a herd of musk oxen. This is a forest in Greenland, a little birch and what have you. Musk oxen are, you know, sort of the same size and shape as a minivan. They corner better. Sorry. Okay. And when I was much younger, now we send students and postdocs to the field. When I was much younger, I used to get to go myself. And so we would get on these big planes, the military airlift, and we'd go up in the middle of Greenland, and we'd do ice cores. And you can just barely see in the light here, this is midnight on the 4th of July. And this is a 100-foot drill tower with this fog over it. We are 2 miles up on the ice. We are 200 miles from the nearest rock, and we're doing climate science. And at the time I took this particular picture, we had been there a month without resupply. So the newspaper was actually a month old. And some of you are aware of this, but it was perfectly fine, okay? Now, this is a good day in Greenland. You'll notice the label, because this is a bad day in Greenland. Just enjoy it, you know? What can I say? And we were up there drilling ice cores. So there's this 2-mile pile of old snow squeezed to ice with a record of climate history in it. And so we get people like Kurt Cuffey here and Wanda Kapsner, and this is in our secret under snow laboratory, and you go down and you get a core and you measure it, and you get another one and you measure, and you do this for 2 miles of ice, and you get 100,000 plus years of climate history. And then from those you can tell stories of what happened. And I'm going to show you a little bit. We turn all this beautiful ice into wiggly lines. And we love wiggly lines. And so this is 10,000 years ago, and this is over to 1989 today. And the red snowfall, the green is temperature. This is not the world, this is central Greenland, but it looks like a lot of what happened all around the North Atlantic. And what you see on here is a very broad arch over 10,000 years that is actually linked to features of Earth's orbit, as you probably know. So if I'm the Earth, and there's my North Pole, and you're the sun, each of you is the sun. If my North Pole stuck straight up, I could never get a sunburn on my Arctic bald spot. But as you know, it is tipped over, and it tips a little more and a little less, and that takes 41,000 years. It's wobbling like a top. And this gets more sun at the pole and less at the equator, and this gets more at the equator and less at the pole, and then it does this, and then it does some other things. And so this broad thing is Earth's orbit. Riding on the back of that are volcanoes blocking the sun. There are changes in the brightness of the sun. There are changes in how the ocean circulated, and maybe some other things. The last ones have names. And they have names because they mattered to people. People had enough memory to say, wait, the climate is different now, and that is changing how I live. And so they gave them names. And so here is the medieval warm period, and here's the little ice age. And so if you ever get the chance to go to southern Greenland, this is very tip of South Greenland, you may recall the story that during that medieval warm period, people had settled in Iceland, and then they settled in Greenland. It was always an advertising campaign. Iceland is green and Greenland is icy, but there's a little bit of green around the edge. And if you get the chance to go there, this is the cathedral at Valsey. Okay? They built this in the 1300s. It's this beautiful stone two-story church. Its last known use was in a wedding on September 14, 1408. Some people had sailed over from Iceland. They witnessed a wedding. They went back and they reported on it in the writings in Iceland. And shortly thereafter, this beautiful church was abandoned, and it's been sitting there in the meadow for the last 600 years. Okay? And what got them was that. There's a lot of things. There may have been some soil depletion, there may have been some economics, but they're trying to live like European farmers on the side of this fjord. The ocean starts freezing, the bishop has troubles getting through the sea ice to get to the church, and other things are happening. The native people, the Tuli Inuit, were fine during this, but the European farmers said, screw it, we're out of here. And they became what we would now call environmental refugees, and they left their church and went either to Iceland or somewhere. Okay? So that sort of 1 degree wiggle was enough to affect people who were living right on the edge. Now, I'm emphasizing that. You will notice that I have carefully whited out this. If that wiggle is enough to affect people, what do you do with that? And this is real. That right there is 18 Fahrenheit or 10 Celsius in about 10 years. Pretty much everybody on the planet got a new climate right there. Some places got warmer, some got colder, some got wetter, some got drier. This was not a greenhouse gas force thing. This was a change in how the ocean and the atmosphere circulated. But it moved a lot of things around. And so very, very rapidly, processes ultimately linked to the orbits, but feeding off of them in very complicated ways, gave rise to this big jump. Okay? Now this goes back to 17,000 years. If I take that previous plot and put it on here, you'll notice something that it was sort of a weird world, boing, 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 and the climate goes, And right where the climate goes, all around the world, people start agriculture. Okay? This is an interesting thing. So these are hunter-gatherers. Here we start farming. And so I'm going to zoom back in on that, blow it up, and I'm going to tell you a story. All right? Now, here's my necessary qualifier. I'm a geologist who does ice, who studies climate. I'm not an anthropologist. I'm going to tell you some anthropology. I'm going to have people in this story. All right? Now, later I'm going to tell you CO2 is a greenhouse gas. CO2 is a greenhouse gas. If you want to argue about that, you should go home and look in the mirror for a very long time. Okay? Here I'm going to tell you what people did. I will guarantee you that this is not the full story. I can't tell you if people are never as easy as one equation. But I believe what I'm going to tell you is accurate. It reflects some of what mattered to these people. So I'm going to walk you through this and ask when it was a decent time and you're a grown-up, what was life like back here in the hunter-gatherer world, and what was life like here in the agriculture world? Okay? So let's see what we can do. Hunter-gatherers for a long time, climate settles down, and then we switch to being farmers. And what happens, okay? If you're a hunter-gatherer, what do? You eat a few berries, you dig up some roots and grubs, you wander on down the road, you go with the flow, it's pretty easy. What do you do if you're an early farmer, you spend the summer scratching the dirt with a stick? I have spent a remarkable amount of time with a hoe in my much younger years. A hoe is easier than a stick because it's sharpened, but this is miserable, I gotta tell you, okay? This one, right, what do you eat over here? The food pyramid. They keep trying to make us eat like this, okay? What do you eat over here? Well, maybe, sometimes you squeeze something out of the cow, or sometimes the cow dies, but otherwise, what do? You grow grain and you grind it up and you eat it, right? So you live on gruel a lot of the time here. This is probably the most important one. Right, if you were a hunter-gatherer and you get a bug and you do it behind the tree, you come back in a year and the bug is dead. If you're a sophisticated early farmer, you're pooping in somebody else's drinking water. And if you're an unsophisticated early farmer, you're pooping in your own drinking water. And you settle down with your diseases and you're just wallowing in them for a lot of time. And so what you find is the healthy people that got grown up in good times are living a pretty long health, and they're tall, and then what happens is you get some bad things, lots of bad things. And yet, what happens all around the world, in Central America, in South America, in China, in the Middle East, as soon as the climate is sort of permissive, people settle down and they say, I would rather have pooping in my drinking water and eating gruel than living like this. Okay? And that's a weird thing to me. And so this, why in heaven's name would you do that? You will get a lot of answers from a lot of people. I think most of the answers ultimately collapse to being sort of the same thing, which is basically that the world was full of hunter-gatherers. And if you had a bad year, you couldn't just go hunt and gather in the next valley over because the big rock tribe lived there and they wanted your valley. There isn't that much in a whole lot of places that we eat. If you can imagine being dropped in a Missouri forest at the start of winter and say, what are you going to eat? Right? There's a couple deer, but not enough to run us. And yeah, you can gnaw a little bark. Yule Gibbons used to say, ever eat a pine tree? Many parts are at. It's really hard to live on a pine tree. And so in point of fact, probably the world was not only full, it was overpopulated. When our ancestors first get to the Americas, what did they find? Mammoths and mastodons and horses and all, stakes on the hoof. And what did they do? They contributed to extinction of those. So they probably are lowering the carrying capacity for hunter-gatherers in a world that is overpopulated given what they do. When the population may have been a few tens of millions, it may have been only a few millions. With what they could do, with the tools they had and the knowledge base they had, maybe a few million people is the total carrying capacity of the world. We are now a few billion. If you think about going back, the next 1,000 people you meet, one survives. Right? You get 20 from the university, something like that. And it might not include any of us in this room. And so the sort of what we've built and what we've learned, what we've taught, what we know, these are not optional. They're absolutely unequivocally essential. And we have gone, you go down to the market. You look at what we had outside here. We had donuts, for goodness sakes, right? You go to the market and you got grapes and you got melons and, we've rebuilt the garden and we have health care and it's just truly amazing that we've done this. But we've done it by learning, by teaching, by growing, by building, by getting along with each other. Okay? So I think this is really important. Somewhere in my pocket here, this is a fascinating thing to do sometimes, right? There's my cell phone, okay? Go into a school class someday and pull it out and say, okay, what is it? Oh, it's a cell phone, or it's your smartphone, or it's your phone. And the people up front will look at it and they'll say, it was a little one, isn't it? You're not very cool. Say, what it's made of? What's it made of? You get this long pause. I had a very bright student once. I did this, right? I'm standing here. It's 5th grade. I'm standing here. What's it made of? And finally the student says, cell phone parts? Said, what are their cell phone parts made of? Plastic. A little bit of oil that goes into the plastic. And sand. A little bit of sand that goes to make the silicon and the chip and the glass. And the right rocks. The rocks with the rare earth elements and the copper and what have you. This is sand, oil, and rocks. The right rocks. And that's all it is. Except science and engineering, right? The GPS has relativity in it. Einstein is in my hand. And without relativity, it would not work. And the computer has quantum mechanics in its design. And so Feynman and Bohr and Heisenberg are in my hand. And we in the geology department use our knowledge of continental drift to help find those right rocks. And so Wegener is in here. Right? This is science and engineering and a little design and marketing writ large. And if you can imagine taking the sand, the oil, and the rocks, the right rocks, and giving them to other groups of people, the Senate, and say, please turn the sand, oil, and rocks into a cell phone. Right? You would wait for all eternity for that to happen. But science and engineering have done it. And yet, I can tell you with very high confidence that we have leaders who will take this and tweet out that scientists don't know what they're talking about. And I have gotten, right? I have gotten the emails that say, you scientists are evil liars. I hope you personally suffer. I'm going to find you. I'm trying to get you fired because you scientists are evil liars and you don't know what you're talking about. And the irony of doing that with a cell phone seems to be lost somehow. Okay, so let me go from that. Science works, right? Learning works. This university is not optional. It is essential. And let me go to that. How do we keep doing this and do it better? How do we live well in a way that our children and their children and their children and their children can live well? And we call this sustainability here, and most of us have sustainability initiatives somewhere or another. Of the issues, there's a lot of them. Getting along with each other, water, food, big grant to make corn better just came in here, right? So there's a lot of things. The United Nations said probably energy is the single biggest of many big issues. How do we live well so our grandchildren can live well? And so I'm going to walk you through the energy story. This is not the only one, but I think it's a really, really important one. So if you got the big donut this morning, you're probably over your 2,000 calories for today. I'm sorry. But, right, a human diet, they often calculate on 2,000 calories per person per day. That turns into 100 watts, right? So what I can do is about the same as the light bulb up there. If I were riding a bicycle to make electricity to run the projector, I could do that, but I'd be out of breath. That's all you can do for yourself is 100 watts. You're 100 watts, 2,000 calories per day. But I don't have to run the light, and I don't have to heat the room, and I didn't have to cook the donuts, and I didn't have to plow the field, and I didn't have to, So we love all this other stuff that is done for us, and we do not hoe all summer so we don't starve to death in the winter. We have tractors that are run by diesel. And if you add up all the energy use in the U.S., divide it by the number of people, and convert to these units, it is about 240,000 calories per person per day. What you can do for you is 2,000. What is done for you is 240,000. It is like more than 100 people to do what we tell them when we tell them. And they do it. They don't argue. And it's about 85% fossil fuel right now. And we love it. Be very clear. This is a great thing for us in a whole lot of ways. We have this long history of finding something to burn, burning it way faster than nature makes more, hitting a crisis, and then trying to find something else to burn. So I come to you from Pennsylvania, Penn's Woods. They said when European settlers first got to Pennsylvania, a squirrel could go up a tree on the Atlantic coast and stay in the trees to the Mississippi. It was trees all the way across. The first forester of the Commonwealth of Pennsylvania was a fellow named Rothrock, who came from my school at one point. He wrote about the Pennsylvania desert. Now, it wasn't a desert, but there were essentially no trees left in the entire state of Pennsylvania. We have 1 million deer now. There were essentially none. We have some elk because we re-imported them from up above Boulder. We chased out we're Nittany lions. I have little Nittany lions on here, right? There's no Nittany lions. There wasn't anything to eat, and there wasn't a tree to do it behind, right? We cleaned out the state completely. And it wasn't just us. I'll show you a picture of you later. But, you know, and part of it was this. So my university was founded up the hill from the iron furnace. And the east was built of Juniata iron, and we were turning red dirt and limestone flux and charcoal into the iron that built the east. And when it was running, it would have looked like this, and there would have been 100 people taking care of it, this whole little town down the hill. And it was powered by trees. And they take the trees and they make a big pile and you bury it in dirt and then you burn it with not too much oxygen and you drive off the water and other things. What's left is charcoal and that burns better. And after they bury it, you're burning it, and if something breaks, you got to get up and patch the hole so it doesn't all burn up. So somebody would be sitting on top of here hoping they don't fall through into this hellish fire going on underneath. And it took trees. And so this is actually a picture of Missouri, 1 mile east of Doss, Missouri in 1938 from the National Archives. Pennsylvania looked just like this. Right? You cut the trees, you turn them into a pile, and you make charcoal out of the pile. A furnace and blast took over a half a square mile of trees a year. There's 100 people taking care of it, and they cook, and they have houses, and they heat in the winter. So you can figure a furnace and blast is a square mile of trees a year. If you go today to Pennsylvania and you find a map of Pennsylvania and you ask, where are the places where the name furnace is still on the map, we haven't forgotten. Okay. Each of these is a furnace, and there's a bunch more that are no longer there. Each of those in blast is a square mile of trees a year. These are forges, Valley Forge and other forges, where they turned the pig iron into valuable things, another square mile of trees. Right? The trees were gone. The idea that we go back to trees when we run out of fossil fuels is absurd. They don't grow anywhere near fast enough. Okay? Now, if you've ever tried to read by firelight, it sort of flickers. Candles aren't a lot better. People used to do other things to try to read at light. They'd use biofuels like camphene, but it sort of blew up a lot and burned things down. And rich people used whale oils. You burn whales. And so this is the history of whale oil production in the Yankee fleet, 1800 to 1880. And this is a complicated story. There's a civil war in here. The fleet is crushed off of Alaska in the sea ice. But what's the fleet doing off of Alaska in the sea ice? There's no whales they can catch closer to home anymore. And you see peak whale oil right there. Price above. The low spot, as they got better, they learned how to do it, they drove the price down. And then scarcity started. It's $7 a gallon in modern money. And then scarcity starts hitting, and once peak whale oil hit, it goes up to $23 a gallon in modern money. And then they went right up the road from where I live. Oil was leaking out of the ground. And some bright person said, wow, if oil leaks out of the ground, maybe there's oil in the ground. So they drilled the first modern oil well. Now, right here at the peak, there are 10,000 sailors out of New England on ships scouring the world ocean for whales. There's 100 years, 80 years of Yankee whaling in there, they collected about a week's worth of recent oil imports. 10,000 at the peak, 100 years, about a week of recent oil imports. Again, the idea that we go back when we're done with what we're burning now is just absurd. But it's very clear that we have trees and whales because we quit burning them. And we quit burning them because of that oil well. And so this is fascinating, right? This is published in Vanity Fair in the year 1861. This is an editorial cartoon. It is a grand ball given by the whales in honor of the discovery of the oil wells of Pennsylvania. And up here, the oil wells of our native land, may they never secede. It's right before his New York publication, right before the Civil War. Oil's well that ends well. All right? We have trees and whales because we're burning fossil trees and fossil algae. And it really is about that simple. Now, we can't keep doing that. Right? First oil well, oil's leaking out of the ground. There's a few of you in this room who are gray enough that you remember when there used to be a situation comedy on television about our energy system. Right? It was a story about a man named Jed. And he was a poor mountaineer, and he barely kept his family fed, and one day he was shooting at some food. You remember it? Up through the ground come a bubbling crude. Oil, that is. Right? You could make that show because oil used to be pretty easy to find. What are they doing in the Gulf with the blowout from BP? Why are they spending millions in deep water? The easy oil is gone. There's a few drops hidden in a couple national parks, not many. But there's a lot of mountaintops that haven't been taken off yet. There's a lot of places that haven't been fracked yet. There's a lot of hard to get left. But the easy stuff really is gone. Nature saved it over a few hundred million years. We burned it over a few hundred years. We're burning it about 1 million times faster than nature saved it. And so there is no choice. We cannot make a choice between fossil fuels and something else. It's only when we switch, because we have to switch. You can build the renewables now, or you can take the mountaintop off and then build the renewables, but there isn't really a third option. Okay? And then that comes to this one. Before Wegener did continental drift, before Einstein did relativity, before Bohr did quantum, we actually knew from Arrhenius that our fossil fuel CO2 would change the climate. This climate science is not some newfangled stuff like quantum mechanics and relativity. It's older than that. The physics really got worked back by the Air Force right after World War II. And the Air Force was not doing climate change. One of the jobs the Air Force brought from World War II was making sure bad guys didn't bomb big cities. And one of the ways you do that is you make a heat-seeking missile. The enemy bomber has a hot exhaust. It emits infrared radiation. You follow the infrared radiation. You fly up their tailpipe and explode and make sure they don't get to your city. But if you put the wrong sensor on your heat-seeking missile, the infrared radiation is soaked up by CO2 in the atmosphere, transferred to other molecules in collisions, and you can't see the target. And so the Air Force said, we need a bunch of physicists to figure out how things work in the atmosphere. And they hired a bunch of physicists, and they sent them up to Hanscom Air Force Base and said, figure this out. And they did. And they make good heat-seeking missiles that work. But I can tell you with really high confidence, even on this gray day, the sun heats the Earth sends infrared to space, CO2 absorbs some of that and transfers it to other molecules in collisions, and that warms the air. And there is more heat being absorbed from the sun-warmed Earth than being absorbed from the hot exhausts of enemy bombers. And so this is a satellite image. The Earth is sending energy that we receive from the sun back to space. And this is the energy going back to space. And this is what CO2 is taking out. And if we add CO2 to the air, it takes out more. And we are adding CO2 to the air like crazy. What we throw away at the curb for the trash collector is about 1,000 pounds per person per year. What we put in the atmosphere from our fossil fuel is about 40,000 pounds per person per year. And so we are raising CO2 CO2 blocks energy, and more CO2 blocks more. And it's really about that. Okay? Now, I could walk through. I teach the course. I wrote a book. I did some TV. There's lots of people can do this too. It's not just me. But we can walk through the whole story with really high confidence that we are raising CO2. The CO2 is causing warming. The warming is occurring. You will meet people that say, I understand that climate's changing, but isn't it natural? Over the last 30 years, the sun has dimmed a little bit. We have blocked the sun with particles. If you actually wanted to get the best estimate, the central estimate, how much of the warming that has occurred is because of our fossil fuel, because of our greenhouse gases, it is more than 100%, because it is warmed despite the sun dimming a little bit. The pattern is what we expected. It confirms our understanding, and our understanding is if we frack it all, if we take off all the mountaintops, we can cause a whole lot bigger changes than we've seen. Okay? We don't believe in global warming, except in the way you believe in gravity. Right? It is, it's physics. You cannot invite someone in here to tell you the other side. There is not one. Science is the best we humans have come up with. There are people who will tell you that I am being too alarmist in what comes next. There are people who will tell you I'm not being alarmist enough. There's a whole lot of arguing about what is a wise path forward, but there's not another side. And if you were to go and find the skeptic literature and start looking for anything coherent in it, you will not find it. You will find criticisms of various quality and quantity, but there is not another side, and you cannot invite the other side in because there isn't one. Science is the best that humanity has come up with, and you just have some nagging suspicion in the back of your mind that science works. Okay? Now, with that, what does it mean? Okay? In the short term, there's still variability, El Niños and La Niñas and so on, but long term, there's a bunch of stuff coming as we crank up temperature. I'm going to lean on a couple of these in here. More floods and more droughts. When the rain comes, it can come really extremely. It can dry faster. You all sort of know this one, right? All winter, the tomato patch is damp. In the summer, you have a gully washer, and 2 weeks later, you're watering the tomatoes, right? More variability in a more summer-like world. You don't have to get nasty diseases, but, you know, you lose a defense line. Sea level rise, virtually unavoidable. I'm going to show you this one. It's a paper published last summer in the Proceedings of the National Academy of Sciences. This is one paper, but it echoes results from several other papers. Right? You probably know that there's a little bit of unhappiness in certain parts of the world, and that Syria is one part of that world that's unhappy. It is very, very clear that Syria had a lot of unhappiness before the recent drought. No one in his or her right mind is going to tell you a drought caused ISIS. But I think everyone who's looked at it will say a drought made things worse in a place that was already pretty unhappy. And that then some threshold in society was crossed with help from the drought and other things that led to crumbling. And for a long time, the climate models have been clear that this is a place where drought will become more likely with warming. And so you'll get the question, did we cause this drought? We loaded the dice. The drought came up. It's a very extreme drought compared to what's been happening there. An already unhappy place got a little more unhappy. And now you have arguments in all the major, Europe, the US are arguing about who do we let in and what does our border look like because of something that crumbled over there. And we probably have a little fingerprint on that. This is a projection of how drought changes if we keep burning into the future and releasing the CO2. Green is actually projecting less drought. So if you were up in Siberia or, running across the north coast of Canada there aren't that many people up there. Where most of the people are, you'll see is yellows and reds and purples, which is more drought. And in particular, if we zoom in on a place where human-caused climate change is probably already contributing to drought, what do you see? A lot more drought. Now, whether those people are going to be allowed to migrate to Siberia, whether they will find soil and croplands when they get there, whether these people are going to actually make it to Canada, and what the wall looks like right there is an interesting question. Okay. Some of our best military leaders, I know a couple of these gentlemen and persons retired, so the CNA Advisory Board, have looked at this, and they're very clear. They said climate change alone did not cause the conflict. And this applies to Syria, this applies to North Africa, this applies to Mali. Climate change alone did not cause the conflict. It certainly added environmental stressors. Making it hard for people who have it hard doesn't make them happy. Okay. This came out last year from the World Bank. Climate change could force more than 100 million people into extreme poverty by 2030. That's only 100 million in a world of 7 billion, but you know, yeah. Okay. You'll meet people routinely who will ask, well, how can you decide what's the best temperature? I can't. Right? There are places that are so cold that warming them will make you happier. There are people who hate snow and hate winter and would like it to be a little warmer. There are places that are so hot that making them hotter is going to be really pretty hard. This is a recent attempt. There have been a few such attempts. This is just looking at the economy. And blue is a place that a little bit of warming would actually help the economy. There's short-term costs and displacements, and it's hard to live a native lifestyle and so on, but you can grow a bigger economy in a warming world. But the reds are places where warming would hurt the economy. And you'll notice that we're actually on the red side, and most of the world's people and most of the world's area is on the red side, and especially down here. And that's starting from where we are now. Okay? And then you come to this one. So per person, the redder it is, the more we're changing the climate. Not much, a whole lot, a whole lot, a whole lot. If you then, this is a fairly complicated effort. This includes that economic looking and some other things, but this is an estimate of how vulnerable people are to the changing climate. If you have winter and bulldozers and air conditioners, a little warming doesn't hurt much. And so the people with winter and bulldozers and air conditioning are sort of colored blue here, not much worry about the near-term climate change. The people in red are colored, you know, making it warmer isn't going to help them, and they have difficulty dealing with it. And so if you take these two plots, and you look at them and say, these people in red are changing the climate, and these people in red are suffering from the changing climate. And then you say, okay, do I believe in the golden rule? And so there's a number of persons, whether it be Jimmy Carter or whether it be Pope Francis, have looked at these two plots, and they've said, I really don't like those two plots. And so Pope Francis said, it seems clear to me also, climate change is a problem that can no longer be left to a future generation, because that plot is interesting. In case you're worried about you, blue is less drought and you know, brown is more drought. And whether you're worried about us or what, you know, so, okay. This is probably very important. First degree of warming is pretty cheap. Right? We've dealt with a variable world before. We're smart. We figure things out. Farmers are not kicked away immediately. You know, you adapt to what's going on and you handle it. Right? But we've already had the first degree of warming. 1 degree, by the way, is 1 degree Celsius, which is 1.8 Fahrenheit. The land warms more than the ocean, so, you know, 2 or 3 Fahrenheit, something like that. The second degree of warming starts to move you outside of what we're accustomed to. Your crops may not work. You may need some lower chill varieties. You know, I start growing different raspberries and daffodils in my yard because the ones I'm used to are not getting enough cold in the winter to make them work. But I can borrow them from somewhere else. And so the second degree of warming starts having more impact, but we're already committed to that one. With fairly high confidence, it's hard to stop much below 2C. Right? We're arguing about 3, 4, and 5, and you start getting to the point where right now, we don't know of any crops that like it as hot as you will be in some parts of the world. And maybe crop breeders will figure this out, but this is already in the crop breeding portfolio. And we don't know of any that actually will be happy at those temperatures. And so as you start moving outside of experience, we're arguing about the costly degrees. We've used up the cheap ones, and we're arguing about the costly ones. In the sort of worst case, by the time the younger students in this room are really old, you might start to have places on Earth that going outside is fatal. Right? So we know you do not leave your puppy locked in a car on a hot summer day in Missouri because they will die. There is no place on Earth now that if you're sitting still and you got a breeze and some water that you have to die of heat. By late in this century, under a burn-it-all future, we might start to get there. Long before we get there, it gets hard to work outside. It gets hard to be comfortable in a lot of places. And so it starts to be real heat stress by late in the century. Okay? You will meet people, good people, careful people who say, uncertainties, 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 right? And that scares me because the uncertainties are mostly on the bad side, right? What do we know? You can't build this with a hammer. It takes getting an amazing number of things right, but you could break this with a hammer. You can't build this building with a hammer, but you could break it with a wrecking ball. You sit there and say, okay, is there much chance that just by turning up CO2, we turn the planet into the Garden of Eden? No. Is there some chance that we break things we care about because it's a big hammer? Yes. CO2 is plant food. Plants like more CO2. They grow better with more CO2. We've had that in our assessments for a very long time. That's not news. And maybe it'll help a little more than we expect, maybe a little less. But there's no way that just cranking up CO2 makes everything perfect, because you got to have the water right, and you got to have the temperature right, you got to have fertilizer. But if it gets too hot, your plants can die. And if it gets too cold, your plants can die. And if it gets too wet, your plants can die. And if it gets too dry, your plants can die. My dad used to kill my mom's flowers by over-fertilizing them. Too little fertilizer can kill them. If the pollinators don't come at the right time, they go down. If you get an invasive virus or an invasive smut or an invasive insect or an invasive weed, it can kill them off. You look at the uncertainties and we say, oh, CO2 makes them grow better. Maybe a little more, maybe a little less, maybe a lot less. It's too hot, it's too cold, it's too wet, it's too dry, it's too invasive, it's the wrong pollinator. What do the uncertainties look like? They're on the bad side. I gave the talk yesterday on sea level rise. We expect about this much in a burn-it-all future by 2100. The uncertainties, it could be that, and it could be out of this room and up on the next floor. They're mostly on the bad side. The less that you trust me, the more you might worry about putting up 20 tons of CO2 per person per year in the US when we know that affects the climate by physics that go into your heat-seeking missile. Okay, so now can we go somewhere good? Are we doomed? Is we running out of things to burn? And you know the answer, that's why you're here. But at any rate, so let me show you this. I swiped this plot from Pulley et al. In Science. This is where the 2,000 calories per person per day comes from. So orange up on top is croplands. The darker colors, more of the total area is used for croplands. And so we grow food on the orange up here. Down here are places that we can't really grow food as farmers, but grass can grow, animals can eat the grass, we can eat the animals, so we can have grazing lands. So we have changed everything in color on this plot to get us those 2,000 calories per person per day. Now suppose that we took off-the-shelf, existing, shovel-ready solar cells, and just for illustration, I'm going to put them in the Sahara. You would not put yours in the Sahara, but just for illustration, what would be necessary with existing technology to supply more energy than all of humanity now uses outside of us? So this is what we changed for 2,000 calories per person per day. This would supply more energy than all of humanity now uses with existing shovel-ready technology. That's off the shelf. Now that is a scary number of solar cells. Don't kid anybody, this is 30 years. But it's doable. And maybe they'll improve solar cells a little on the way, because that's surely happening now. I'll show you this one. When we did our TV shows, we had these Texas ranchers in it. And the Texas ranchers love this. Wind has been with us historically for a while. So I'll start you with Abe Lincoln here, right before he's president. Abe Lincoln is on the stump giving a speech about learning and science and patents and engineering. And at some point in the speech, he says, wind is an untamed and unharnessed force, and one of the greatest discoveries will be the taming and harnessing of it. And so now these Texas ranchers put 5% of the ranch in wind turbines. And then they get what they call mailbox money. You go to the mailbox and you get money. And each of these turbines is about $5,000 per turbine per year. And that actually often pays a little better than the steers do. Right? And they can still have 95% of the ranch for the steers, but this is paying really well. If we go out and we put a wind farm on the windy parts of the plains and deserts of the world, that's more energy than humanity uses. So you look at this, and I can talk a lot more about ways forward and so on, but you look at this, and we have this long history. We were hunter-gatherers of food, and we switched to farming, and then we figured it out. We are still hunter-gatherers of energy. We're still looking for the next big play. But we now know, for the first time, how to become farmers of energy. And the full scholarship, taking consideration of how much we love fossil fuels, how much good they do for us, and what's available for the future. The full scholarship says that if we turn the students loose, we end up better off. And there will be new industries, and there will be new jobs, more jobs, and that eventually we can build to a sustainable future. And that it will not only help the environment and the golden rule, but it will also help the economy. And we can talk about what that means in the questions, but what I'm going to do is leave you with a picture I took in Greenland. Can we have a world with icebergs and rainbows? Yes. Thank you. Okay.
Excellent. All right, well, if there are any questions, please raise your hands really high. We're going to be running 2 mics. And
we have
please,
a gentleman in the back right up there. Yeah.
and please be sure to speak into these mics. These are being recorded. Thank you.
Exercise. All right.
So I have 2 questions. One is the last part. One, how long do you think it's going to take to build all of these wind turbines? Is it
Right,
feasible?
so probably, I like to say 30 years. We could do it a little faster, we could make it 40, but so, you know, in this sort of, do we need a whole 100? No. Could we do it in 3? No. What's between 3 and 100? 30. Okay, so probably something like that.
And then my second question, what do you have to say to those who think that the climate change is basically a repetition of history? Because we know that like climate has changed up and down as far as like we've had ice age warming. What do you have to say to that?
So there's 2 or 3 pieces. There's a wonderful question about it. So first of all, we actually are looking what's going on. Volcanoes block the sun is changing, we're measuring the sun, oceans are changing, you know, we're measuring all of this. And what we find is that over the last 30 years, nature has tried to cool it off a little bit. So the natural forcing has been towards cooling. We have tried to cool it off a little bit by blocking the sun with particles from our smokestacks, by cutting some dark trees and planting more reflective grasslands. And so we have done some things that cool it off. Nature has done some things that cool it off, but it's warmed up. And so, but the other one, which is fascinating, nature has changed climate. And when we look at the whole, if I'm teaching a class right now, and if you took the whole class, what would come out in the end is when nature has changed things, sun, CO2, other things, climate has responded a lot. And living things have been changed hugely when the climate changed. So climate is very consequential for life. And of the many things that have driven climate change, CO2 has been the most important. And nature has changed CO2 in the past, And plants and animals have died, they've become extinct, they've been forced to migrate and other sorts of changes. All we're doing is something sort of as big as the biggest things that nature has done, but faster. So it's one of these, it's very easy to say climate has always changed, and then lead into, so we shouldn't worry about it. But when we go back and look at the history of climate, right, we've always had fires, but arson exists. And the arson investigator better understand natural fires. And the arson investigator probably is very worried about fire because they understand natural fire. When we look at history of climate, when nature's changed CO2, living things have been forced to change hugely and greatly. And we're changing CO2 as much but faster. Great, thank you. Yes?
So you mentioned wind turbines, but
Right.
so you mentioned wind turbines, but from my understanding, solar energy seems to be more promise. I mean, back in the 70s, when essentially Carter left office and Reagan took office, he took down the solar panels off the White House, and they're now, my understanding, is sitting in some museum in China is pretty much outdated compared to what they have now available and Germany's basically produced. So could you comment whether this, solar energy or solar panels is more the way to go compared to the wind turbines, in your opinion?
So very good question. The history, when I started writing the book that turned into the TV shows that turned into the little logo in the corner was 2009. And in 2009, I could not, with a straight face, say that solar was competitive for much of anything. It worked really well in my solar calculator. And that was sort of it. And today, you see all around the nation battles going on because solar has gotten cheap enough that it is undercutting the business models of existing utilities. So from 2009 to 2016, everything has changed. And that learning curve, there's a learning curve on wind too, but the learning curve on solar has been tremendously steeper. And so solar is dropping so fast. Eventually, it's quite clear. So in round numbers, if we got 0.01% of the solar energy that reaches the Earth, that would power all of humanity. Wind, more or less 1% of the sun becomes wind. So we have to get 1% of the wind's energy to power all of humanity. It's easier to get 0.01 than it is to get 1. And so ultimately, solar is probably the biggest deal. In the path to getting there, it's pretty clear that wind is economical. Wind is, you're seeing wind undercutting business models because it's so cheap. There are places people are trying to redistribute load by doing things like giving away wind power at night for free. You pay nothing if you use it at night. And so wind is almost certainly a piece of the story going forward. Eventually, you're going to see mixes that work for people where they live. Some people use some waves and tides, but 1% of the wind goes into waves and currents. Now, tides are slightly different, but for waves and currents, 1% of the wind goes into them. That's not quite enough. We'd have to get all of that. And so sun is far and away the biggest resource, and it is likely going forward to be the biggest source. Wind is likely to be important. And then other things are likely to be important locally. We may do a little bit of geothermal. We may do some currents and tides. If the sea is rising next to your city and you have to build a wall, you can build a wall that the waves bang against, or you can build a wall with generators in it and get some power out of them. So it will almost certainly look like what works for people where they live, but it will have more sun in it than anything else eventually.
If CO2 helps plants and plants produce oxygen, is there a possibility that these two will balance out in our atmosphere?
Right. So the question, there are several lines of evidence. I said we are raising CO2. I had a bullet, right? And there are a whole bunch of lines of evidence that go into that. One of those is that oxygen is dropping. And so we are burning so plants are growing a little better from the CO2, but we're burning an immense amount of dead plants. And what does that do? If you remember the story, the plant took CO2 and H2O and it made plant. And the CO2 goes into plant. The plant goes into buried in the mud. It gets cooked by the heat of the earth. That makes fossil fuel, but the CO2 is still in there. When we burn it, the C is in there. When we burn it, we take O from the atmosphere, we add it to the C, we make CO2. And as the CO2 goes up, the oxygen is going down. And one could, you know, you will meet someone who says, oh, the rise in CO2 is from the volcanoes. Well, first of all, we go out and measure what comes out of volcanoes, and we're 100 times more than that in round numbers. But if a volcano makes CO2, it melted something. That doesn't use oxygen. If a fire from a fossil fuel makes CO2, it uses oxygen. So the rise of CO2, if it's from volcanoes, oxygen is flat. If it's from burning, oxygen is falling. What is happening? Oxygen is falling. Now, there isn't enough fossil fuel left, we're pretty confident, to change oxygen enough that we will have troubles breathing. So that's not a worry. But the oxygen is actually dropping a little, and it's dropping a little because it's being used to turn fossil fuels into CO2. Yes?
Yeah. My impression is that the oceans have really been protecting us a lot. They serve as a heat sink. They also buffer CO2 by absorbing CO2. Is there a point at which basically the oceans become saturated and they start not protecting us as well?
Yes. So the point is very good. And yes, the more that we call on them to do, the less that they can do in addition. So we start using up their capacity. Eventually, right now, almost all the heat, and you know this, but almost all the extra heat is going into the ocean. A little tiny bit in the air, and we see that as temperature, a whole lot into the ocean. But as the ocean warms up, more of it will stay in the air. So right now, if we stabilize the composition of the atmosphere, it will warm for a while. Because as the ocean warms, more heat will stay in the atmosphere. And so we will get more warming even if we stabilize the composition of the atmosphere, because we'll use up some of that capacity of the ocean. The acidification is very clearly an issue for living things. When we look in deep time, way back in time, as you crank up CO2 and make it hot, there's less oxygen in the ocean. You know, if you heat Coke, the fizz comes off. All gases come out when you heat water, and that includes oxygen. And so there's less dissolved oxygen. And so you tend to run out of oxygen. One of the ways that nature deals with CO2 is to make fossil fuels. So what happens, you make it really hot, the oxygen in the ocean drops. That means that the worms on the bottom of the ocean die. Now when dead plants fall, the worms don't eat them and burn the plant to get energy. They let it be buried, and that's where fossil fuels come from. And so over time, nature takes CO2 and turns it into fossil fuels by, in part, getting rid of oxygen in the ocean to make them monoxide. Now, in a few 100,000 years, nature will undo what we do. That will take our CO2 and do that and some other things. But when you make the ocean low in oxygen, things that we like to eat tend to disappear. And sometimes in the past, it's gotten so bad that really nasty gases like hydrogen sulfide have come out of the ocean. We don't think we're going to get to there, but if you wanted a worst case scenario, you make these dead zones. The dead zones become euxinic. They have chlorobiacea photosynthesizing in the surface ocean and making H2S, which is a poison and is blowing around in the air. So we can think of bad things, but the ocean very clearly is buffering what we're doing now. You're completely right. Yes.
So you said that a way to fix this is to build solar panels and wind turbines. And my question is, if we have to use energy to build those, and it will take 30 or so years, by the time we build those, will the greenhouse gases and the climate change already be incredibly bad, where if you're sitting outside, you can die from heat?
Right, so a number of things in there. So we think it is very late in this century before the worst of the heat gets. So if we get started really seriously now, in 30 years, we've got a sustainable energy system. We've held warming to 2 degrees. And that avoids the worst of the problems. So it gets, each degree is worse than the previous degree. So stopping at 2 is way better than stopping at 3. Stopping at 3 is better than stopping at 4. So you miss most of the problem. It is true that right now it takes energy to build a wind turbine. It takes energy to build a solar cell. If you build the wind turbine with fossil fuels, you install it with fossil fuels, you maintain it with fossil fuels, and you recycle it with fossil fuels, you cut fossil fuel use by about 95%. because the wind turbine is so incredible at pulling energy out of the air that what it pulls out of the air dwarfs what you use for everything else. In fact, what you would do is you'd build it with fossil fuels, but you'd maintain it and recycle it with renewable energy because now you have a new energy system. And so there's a tremendous gain in moving this way, even though there is some energy investment that goes into building these. So the energy yield, and you will meet people who have this number wrong by 100-fold and more. But in point of fact, the energy invested in building, maintaining, and recycling a solar cell or a wind turbine is very tiny compared to the energy they yield. They have a huge net. So it's actually very good.
Clearly, at this point, we can get a lot of wind and a lot of solar installed. But using wind and solar, particularly at any given point, sometimes ends up with periods where there is not energy coming in. Now, we can store that energy with a variety of techniques. What do you see as the most likely way to store renewable energy?
Right. So the point is very well taken, and thank you. Wind dies, sun sets, right? And so there's a number of things that are being done, and I'll walk you through them, and then I will try to answer your question, but I'll try to get there. So when I started in this in 2009, all of the experts said with confidence, we will never get beyond 20% renewables without serious storage. And a whole bunch of the places in the world have blown past 20% without blinking, without serious storage. So it's very clear that grid operators are learning. And you get there in part by mixing multiple sources, wind, sun, a little hydroelectric helps a lot. A little geothermal could help a lot in some places. You get there by interconnections. So bigger areas have less fluctuations, especially in wind. That does bring up the issue that you sort of want to look at having transmission capability. If you can't move electricity around, then the fluctuations locally are more important. So transmission capability becomes really important. Eventually, you're going to look at having something else. And right now, as you know, it's a gas turbine or something like that. So we have sitting in places, there's coal plants or wind and sun, and they're putting electricity on the grid. And then someplace, there's a gas turbine that is probably sitting there doing nothing. And when the demand goes up, you turn on that gas turbine and you fill in the gap. And that's really expensive because you have to maintain a plant lots of times. You have to invest in the plant. You have to get the bonds to build the plant. But it's not working most of the time. So you're running all that investment over a small amount of energy, not a large amount. As soon as batteries get to the most expensive power on the grid, they're competitive. And you will see getting batteries to the cheapest power on the grid is a long ways off. Getting batteries to the most expensive power of the grid is actually pretty close already. And so what you start getting to is, first of all, storage in batteries. You may see pumped hydro. So, you take water and you pump it up into the higher lake when you have extra power. You let it run down through the hydroelectric plant when you need it. You may see a little bit of building of other things. In the short term, you'll probably see gas turbines. Right? So coal plants have troubles going up and down real fast. Gas is really easy. And so if you build gas turbines instead of coal plants, then you can build lots and lots of renewables and use the gas turbine to fill in. And so you drop your emissions 80 or 90% on the way to 100. Eventually, I think you will see things like, here's one idea. People are buying hybrids, Priuses and things like that. You have some sort of fuel. It may be eventually it may be a biodiesel, it may be something else, and you have a battery. So suppose you get to the point that all of the U of Mizzou vehicles are plug-in hybrids. And Missouri is smart, and you have wise engineers. And so out at the parking lot, you've got a bunch of solar cells plugged in, and you park under the solar cell, and you plug your car into it, and it charges during the day. But the University of Missouri vehicles, when they're parked, have a buy-sell with the utility. And if the wind dies and the sun sets, there's batteries plugged into the grid. And now what happens? The utility says, I need a little power out of your battery, so they buy it. And they pay you for that. And then when they have extra power, they put it back in your battery, and you pay them for that. And it's even a few percent of the vehicle fleet on a buy-sell plug-in system will stabilize an immense amount of renewables. Because in the time over which we buy our cars, 20 years or so to cycle through our cars, there's an immense number of batteries have gone into that, of the kind that people are driving around here every day. I came over in a cab that had some of them, right? And so you start getting this, and when the battery in the Prius is half dead, you take it out and you rack it up in a giant building somewhere and you use it until it's fully dead before you recycle it. And so over the time that we buy our vehicles, the number of batteries in the system is astronomical. And I think you're seeing people are looking at, there is one very well-known wealthy person who is trying to become more wealthy by tying vehicle batteries to home batteries, to grid batteries. And so whether that will be the ultimate winner, I don't think we know yet, but it's clear that that can be done. And it's clear that you can use a battery that's bought for a car for two things, multi-purpose it. Yeah.
Back in the 70s, someone mentioned about solar cells. At that time, we had like 10%. If we got better than 10%, we were really happy. Today, commercial sales get 20%. I would really expect them to go on from there. Not a lot higher, but some higher. Question. I have read that in the past, when there was climate change, that often the CO2 was a laggard indicator. Could you mention that? And then I have one more.
Yeah. So this one, at one point, we had a donor to the university, a very nice person. I had lunch with this person, and we had a discussion. And then some bad emails were published, stolen and published, and this person became very mad at me. And he was trying very hard to get me fired, and it was based on this. He sent a letter, which he copied to me, which he sent to the president and the provost, that said, CO2, on ice age cycles, CO2 lags temperature. This one fact proves that Dr. Alley is a liar. Fire him immediately. Okay? So what happens? The ice ages are caused by features of Earth's orbit. And those features, as I said, there's this one. It nods a little more and it nods a little less, and that's 41,000 years. There's also a wobble that's between 19 and 23,000 years, and then the shape of the orbit gets more squashed and rounder over 100,000 years. And you combine this one and this one and this one, and you get the ice age cycling. But when this was first worked out, when Milankovitch worked this out, he said, all it's doing is moving sunshine around. This has a tiny change in the total sunshine, but this just moves it around. There's more at the pole, less at the equator. There's more at the equator, less at the pole. So he said the ice ages must run away. It'll be cold here, and then it'll be cold here. And then, so because you're just moving sunshine around. And what's bizarre is some of the cycles do this, some of the cycles do this, but the world does this. When Canada gets more sun, the ice melts in Canada, the ocean rises, the currents and the wind change, CO2 rises, and the entire world gets warmer, including places getting less sun. So half of the world gets less sun and warms up. And it warms up because of CO2. And when Canada gets less sun, the ice grows and the currents and everything changes and CO2 changes, and the places getting more sun cool off. So half of the world ignores its local sun and listens to Canada through CO2. But the orbits cannot in any way control CO2 directly. So changing how much sun you get at a point during a season doesn't directly change CO2. You change temperature there in the summer, which changes melting of ice, which changes sea level and glaciers, which changes currents and winds, which changes CO2. So there has to be a path that goes orbits to Canada to CO2. And CO2 has to lag a little bit because of what's happening. But what happens is you start this off, and then the CO2 follows, and then the two go together for a very long time. The analogy I used with this gentleman, which he didn't really like, is the following one. Okay? So suppose, for the sake of argument, that I have in here a credit card. Suppose that I take my credit card from the Visa Corporation and I overspend and I go into debt. They will then add interest. That will make my debt worse. This gentleman's argument, CO2 lags temperature, so CO2 cannot contribute to temperature. Interest lags debt. So interest cannot contribute to debt, so I don't have to pay the Visa Corporation. He was a successful businessman. There's not a chance in heck that he would make that argument. But the mere fact that there's a little lag doesn't tell you anything. The fact that they go together tells you interesting things that we should understand this. When we run it through all of the understanding, we find something starting with sunshine and ending up demonstrating with high confidence that CO2 is really a big deal. So it's one of these that the knee-jerk, simple soundbite is exactly wrong. Many of these. The one about it hurting the economy and a whole bunch of others are the same story.
Don't you think that the willingness of climate scientists to tolerate the deliberate delays in response to climate change prevents people from reacting to climate change as a crisis, as an emergency, in which case, universally, deliberate delay is immoral. You don't wait till tomorrow to throw a drowning person a life preserver.
Okay, so if you did not hear the whole thing, a very, very cogent statement, and thank you, which raised two issues. One is that this really is a moral issue as well as a scientific and economic one. I think that I have not yet met a moral leader or a faith leader who has seriously looked at the science, who was not deeply concerned about this as a moral issue. So I think all of the leaders would agree with you on this who have engaged with it. The question, right,
We start with delay as unacceptable. And if we have to react now at any price, we start, even if we have little red hand volunteers.
Right, so the argument was delay is unacceptable. And you raised the issue earlier about the role of me and other climate scientists, which is a role that, this is one that makes me deeply uncomfortable, okay? So I can tell you, we are Methodists, okay? We go to church on Sunday, and I happen to be deeply committed to the Golden Rule, okay? And as a consequence of being deeply committed to the Golden Rule and having a faith, I am deeply concerned about those maps that I showed you. Now, the question of do I then go out and tell people what to do, or do I give them the science and let them decide what to do? I personally have made the decision that I'm not going to tell you what to do. I will try to give you the evidence in an as engaging a manner as possible that is as true as possible to the scholarship, and I won't tell you what to do, because my impression is that there has been a very well-organized effort that as soon as I, as a scientist, start telling you what to do, I will be marginalized because I'm not a scientist anymore, I'm a political activist. And I believe that this is correct, and we do, so, and I'll step away in a different direction. When Ken did the introduction and he talked a little bit about the National Academy, you talked about the National Academy. If I serve the U.S. National Academy of Sciences on a panel, if I have taken strong public opinions on something, I have to declare them, and they will look at them carefully. That doesn't disqualify me, but it's very clear that as a human, if I come out here and tell you, you must do X, my judgment is probably clouded for the future. So I have personally chosen to try not to tell you what to do. I think this is all of us. I think we have to get it together. So, and your point is very well taken. In a crisis, one needs to get going. I believe there are roles for many persons in this. And like I say, I would hope that if those of you who are concerned about it will take that into consideration when you personally make decisions.
due to time constraints, we're going to bring this to a close. There are 2 questions. You go first, sir, and there's one back here. Thank you very much.
Yes, sir. It's my understanding that parallel to the climate change issues we've been talking about today is a parallel explosion of the world human population. How does that fit into this equation?
Right, so the point is very well taken on population. Our impact on the world is number of people times impact per person. And we can lower impact per person, we can lower number of people if we want to lower the total impact. The most optimistic version, we see very clearly across much of the world that if we can supply 2 or 3 things that people choose to replace themselves and not more without any coercion, without any laws forcing them what to do. They choose to quit population growth. And those things are, first of all, fairly high confidence that your children do not die young. So you don't have to have 5 kids to get 2 of them to live. You actually can have 2 kids and get 2 to live. Secondly is sort of interesting things to do with your life. Cell phones may help with that. And with that is especially some level of control by women of their lives. And if we get confidence the kids grow up in an interesting world where people can make choices, people choose to replace themselves and not more, and population growth will end. It may even drop a little bit. That's the current scholarship. If we don't get those, it's been on an exponential rise, and you know as well as I do that exponential rises eventually end. And whether they end in a logistic sense or whether they end in a crash, yeah. So yeah. And of the things that go in, this is so much, and it is so much learning, and it is so much doing, and it's so much commitment from people to make sure your babies don't die, make sure you have a little food, make sure you can do to something, and make sure people can make choices for themselves. A better energy system will help. It's certainly not all of it. So it is a challenge for everyone, but it is clear that there is a solution that does not involve crash and does not involve heavy-handed governments coming into your bedroom and telling you what to do. That there is a solution, but that solution involves helping a lot of babies and a lot of people to have lives and choices.
Thank you all very much, and this is going to be our last question.
Okay, thank you very much for your talk. This question is somewhat political, somewhat strategic, so if you can't answer it, that's okay. 33 years ago in college, I took a class, a science class, on alternative energy resources, and being 20 or 21, I naively thought that these would happen. And so from your experience in the field, what are the groups, the interests, the concerns that have, I mean, is it simply, quotation marks, bad oil, or is it just some people are making profits and others don't want, or is it fear of big government? Is it just people just didn't see the problem because we are the frogs and it's not the frogs that don't jump out of the hot water, it's people?
So there was a study recently that looked at sort of a dozen, I think it was about a dozen big democracies, and looked at the conservative parties. And this study said the only major democracy in the world that has a party in which the standard bearers are now rejecting the science out of hand is ours. Okay, and I'm not an expert on this, but that was what this study said. Is that so? Most of the world is not quite where we are on this. It is clear that So suppose for a moment that we think about moving forward with a renewable energy system over 30 years that improves the economy and gives more employment, more jobs. Even if you doubled employment, those jobs will go to students who are now here, and some people may lose their jobs, and they are probably people who have companies and mortgages and families and so on. So something that doubles employment is likely to look really bad in the press right now. And so there is an issue here, and people with money have been using it to spin up stories which are not terribly accurate, to be perfectly honest. This particular response, trying to confuse the public, so that they don't make a change has been going on for a long time. The real estate developers of San Francisco were doing this right after the 1906 earthquake. So they were, oh, the stress is relieved and it was a fire, it wasn't an earthquake, and don't worry about it, okay? There's nothing really new here now. The professionalism may be up a little bit. So I'm optimistic that we'll figure out a way around this, but it's very clear that there are a lot of scared people. It's very clear that there are a lot of people applying money in particular places to try to get particular ideas. If you come here, Naomi Oreskes, you will hear a lot about how this has been done and what has happened from the scholarship of the field. And like I say, the tobacco did this, lead did this over lead paint and things like leaded gasoline. It's happened before, but it may be a little bigger and a little clearer right now.
So thanks everyone for coming.
Thank you. Thank you.